So, this is actually one of the good problems. And by the good problems, I mean the problems where you learn a lot of stuff. So you look at this and you're like, okay, I have absolutely no idea where to start with this. So this is one of the things where you just need to see it at least once. But in the meantime, in the process, we will try to motivate it as much as we can. So when I say motivate, I mean we will be investigating this expression and we will see what we can do with it. So here are some ideas. So I start with the x squared plus 14x plus 98. I mean, the numerator is done. There's nothing I can do with it. But perhaps I can do something with the denominator. Now keep in mind, I'm in the exam. I need to solve this problem. I need to get the points. So that's really what I'm trying to do. So I have to do something. I make a good observation. I mean, this is x squared plus 2 times x times 7, right? And then this is something, right? But it would be nice if we just had, it would be so nice if we just had x squared plus 14x plus 7 squared. I mean, by 14 I mean 2 times 7 times x. That would be so nice, right? Because then I can just write this as x plus 7 squared. Well, almost, because 7 squared is to 49, and so I'm actually missing another 49. So 49 plus 49 is 98, and in this case, these two expressions are equivalent. So this is nice, but I still need to, add a 49. I hope that's okay. Remember, we're just investigating, trying to, do something. So maybe I can write this as integral from 0 to 1 of 1 over x plus 7 squared plus 49. So another 49. Now let's not forget the dx, otherwise the integral doesn't have any meaning. And just as a brief note, because we will use this in a moment, these boundaries are always with respect to the variable of integration. So if this is the variable x, then this is an integration from the bound x is equal to 0 to x is equal to 1. Just a brief note, we'll use it in a moment. But I actually think this is very nice, what I have here. And the reason is that I have an inside function. I can look at the derivative of the inside function and I can inspect. By inspect, I'll ask myself the following question. That is, do we have the derivative of the inside function? First off, just to clarify my point of view. So here we have an inside function. So it's x plus 7 composed with x squared. So you get x plus 7 squared. So if I choose u to be x plus 7, then that's just amazing because the derivative of u is equal precisely to the derivative of x. It's the same rate of change. And you could say that the derivative of u is in the expression, it's just 1. So this is very nice and very practical for our purposes. So I can make this substitution now because I can make it, and I will make it because I can. Remember, this is usually how we proceed with integration by substitution. If the derivative of u is in our expression, then you can cancel it out. I mean, in this case, you only have 1, so there's not much you can do. So this is I. I is the integral from x is equal to 0 to x is equal to 1 of what? of x plus 7 squared plus 49 dx. dx is equal to du, and x plus 7 is equal to u. But there is something that needs to be changed about this integral. What is it? Yes, exactly, it's the boundaries. So the boundaries are still in terms of x. So I need to do like this. But then am I done? Of course not, because if x is equal to 0, then u is equal to 0 plus 7, which is 7. Similarly, if x is equal to 1, then u is equal to 7 plus 1, which is 8. So I also have to keep this in mind, because we will use this again in a moment. This is not an easy integral, because there are lots of things to learn from this. Now, at this point, there are really one of two things you can do. I mean, I can also write this as follows. I hope that's okay. So let's say, so it's really one of two cases. It's either number one, and you have a very good photographic memory and you only need to see things once. So when you see this, you immediately identify it as the antiderivative of the arctangent function. So it's either this, well, almost, because you need to do some work, right? This is 49, this is this, but it's fine. You can do some adjustments. If you already know this and if you've seen this before, then you would get the answer very quickly. Here's how you would get it. So I want to have a 1 here. And then I will divide by 49. So I'll multiply by 1 over 49. So here I'll multiply by 1 over 49. There I'll multiply by 1 over 49. I can also write this, I can bring it outside. The integral, of course, this is with respect to u. So here's what I mean by bringing it outside. So I do like this. I made a small typo. So I'm multiplying 1 over 49 by this expression in the brackets. So do not make the small error that I just committed. And then when I do this, when I multiply the whole thing by 1 over 49, then it's very nice, you know? Because the 1 over 49 with the 49 gives me a 1, right? And then here I get division by 49. But notice this. U squared over 49 is equal to what? It's equal to u over 7 squared. So that's what it is. And that is what it is. Okay, then I'll just write this. So I'll write u over 7 squared. Then I can apply the antiderivative. If I have a photographic memory, of course, and I know how to proceed with this. So I would write 1 over 49 on the outside. And then the following. So the derivative of what gives me u over 7 squared plus 1? Is it the derivative of tan inverse of, let's say, u over 7? the derivative of this, so if I take the derivative of this, I would get the derivative of the outside function, which is 1 over 1 plus u over 7 squared. But then this is a composition of the tan inverse function and u over 7. So I still need to multiply by the derivative of the inside function, which is u over 7 prime. In this case, this would be 1 over 7. So I get 1 over 7 times this thing. Okay, that's not too bad. I have here I have 1 over 49. Maybe I can just, borrow one of the 7s, since 7 times 7 is 49. So this 49 I'll write as follows. I'll write as 1 over 7, and then I'll write on the inside, I'll write 1 over 7. I'll write 1 over 7. Well, not here, actually. Maybe I should not write it here. I should write it there. So if I write 1 over 49, and let's say I have a little bit more space, so I give myself a little bit more space to do the following. So the 49, I want to rewrite it as 1 over 7 times 1 over 7. Then it works, because this, when I take the derivative of this thing, so when I take the derivative of this thing, I get tan inverse of u over 7, correct? So the antiderivative of this thing is that thing on the top. This is precisely what I mean. Maybe I'll write this explicitly. Write this down explicitly. So derivative is 1 over 7 times okay. So because this is the antiderivative, then the 1 over 7 stays outside, this one, and this is just the derivative, so tan inverse of u over 7. But I still need to plug in from u is equal to 7 to u is equal to 8. So by definition, I just write the following. So it's tan inverse of 8 over 7. So this happens inside of the bracket, if you're wondering. Minus tan inverse of 7 over 7. And then if I would like to simplify this, by the way, if I would like to simplify this, then I would get 1 over 7 times, well, tan inverse of 8 over 7 is just tan inverse of 8 over 7. But tan inverse of 7 over 7 is tan inverse of 1. And if you ask yourself, the tangent of what function gives you 1? It's, the tangent of what angle, what angle in radians gives you 1? And it's 45 degrees, right? Because in a 45 degree so a right angle triangle with 45 degrees, the 45, then this side is equal to that side. So if you take the tangent, it's always the opposite divided by the adjacent. And if the opposite is equal to the adjacent, like we have here, no matter what angle you take, then you would get the ratio, which is the tangent, to be 1. So that is some explanation. But is this correct? Is it correct to write 45 degrees? Not really. You need to write pi over 4. in radians. So pi represents 180 degrees. Divide by 4, you get, divide by 2, you get 90. Divide by 2 again, you get 45. So this is correct. And it looks like I might be done. So remember, I was doing all of this under the stipulation that I have a photographic memory. But the thing is, I do not. And a photographic memory is a very rare thing to have. So I wouldn't assume that you would have one. So if you're on the exam and you cannot remember anything whatsoever, but you have the patience and the time and the focus to do this, then I would like to show you the way. So where were we? We were here before we got stuck with everything. So, or you get stuck with this and you don't know what to do. There is a general theme or a general idea to get yourself outside of these situations. And so two identities will be your friend. The first one is cosine squared of theta plus sine squared of theta is equal to 1, and tangent squared of theta plus 1 is equal to sec squared of theta. So okay, maybe you don't have a photographic memory, but you remember these two identities. Like this is the bare minimum. I don't know. These are I think these are famous identities. At least the first one. So when you're stuck, you should go to these guys and compare your expression to see if you can get rid of whatever you want to get rid of. So if you have something that looks like, let's say, just for example, say something that looks 1 minus, I don't know, x squared. Then if I choose x to be cosine, then I get 1 over 1 minus cosine squared under the square root. But then 1 minus cosine squared by this formula is sine squared under the square root. But then guess what? The square root cancels out with the square, so you get sine of theta, which is very convenient. Of course, I'm skipping some stuff, some formalities, but I'm just giving you the idea behind this. Here, I'll tell you this, we won't use the first identity, we'll use the second one. So perhaps it's a good idea to only include the second identity. And maybe you can try to pause the video and think about how you would utilize this in this very specific situation to your advantage. Now, assuming that you have already paused the video and you want to use this, then you want to have a 1 here. Somehow. So, want a 1. Then I can just multiply this by 1 over 49 and then 1 over 49, just like I did here. So here I have different motivations. I already know the tan inverse function is the derivative of whatever function I had. But the different motivation here is to use one of the identities. And so I do this, and I multiply by 1 over 49 upstairs and downstairs. I do this, I take the 1 over 49 outside, and here I get my 1, and there I get my u over 7 inside the square. So this is inside the square. We've clarified why this is true. So we would get something that looks like this. So just by wanting a 1, you can go very far. You can go very far until this step. So I think this is already very strong. But then what do you do? Well, here's what you do. So just to make it clear, I won't put the 1/7 here because we didn't really know what was going on. We just put the 1/49 outside. We will use the 1/7 later, but let's say we don't know what's going to happen. So we just put the 1/49 outside the integral, and we have this setup where we have u/7 squared plus 1. Then now I can make my substitution. I use my identity, so I say u/7 will be equal to tan squared of theta, such that when I plug in tan squared of theta here, plus 1, I can remove it and I can write sec squared of theta. And maybe everything works to my favor. Let's see. So this might actually work to my favor. Let me go on. If I want to make another substitution like this one, then here's what I would like to do. I would like to find an expression for a du in order to replace it. So I differentiate both sides. This is u/7 I can write as 1/7 times u. I hope that's fine. And when I take the derivative, I get 1/7 times du will be equal to the derivative of the tangent squared of theta. Now, if you are this far in the video and you still are following, then there is a high probability that you know what the derivative of the tangent function is. By the way, here we don't need to take tan squared, we just need to take tangent, because then when we plug it in, we get squared, and then you would get the 1, and then you would substitute for sec squared. So we just need tangent. That was a small error on my side as well. Now I presume you already know the derivative of tangent. But if you don't, it's sec squared of theta as well. So if you've never seen it, then this is really what it is. So that's very good. It's very promising. Then I can write sec squared theta d theta. And my goal is to replace du. So I can just multiply both sides by 7. Then I would get I'll get 7 sec squared theta d theta for my du. So I can immediately proceed as follows. On the outside I have 1/49. The boundaries are still in terms of u. That's very important. And I now do my magic. So my du goes away. I put 7 sec squared of theta d theta. Maybe I can put this on top. And the magic also happens when I put in my my tangent of theta. Remember, this was squared and added 1 to it. So I will just apply the identity. It's good to reference your work always. Then here's what I get. Tan of theta squared plus 1, we said this was sec squared. Luckily it was. And guess what we have here? Sec squared and sec squared. This is so satisfying. You can't believe it. 24 minutes and 53 seconds into the video, and we reached this. This is an absolute milestone for us. Amazing, just amazing. So this is that. 49 and 7, this cancels out, I get 1 over 7. Then this is equal to, so 1 over 7 on the outside, and then here I just have d theta. I will leave the boundaries as they are just for the time being, and then I'll get so if I integrate something d theta, it's just 1. So I will get theta. So I get 1 over 7 on the outside, and then the value for the integral will be theta. I need to plug in from u is equal to 7 to u is equal to 8. But what is theta? Well, we know that tan theta is 1 over 7 of u. Then probably, if I want to isolate theta, then tan inverse of 1 over 7 of u, which I'll write as u over 7, is equal to my theta. Then I get 1 over 7, and then on the inside I get tan inverse of u over 7 from u is equal to 7 to u is equal to 8. And then by the same argument that we did here, so you would get this, right? You would get tan inverse of 8 over 7 minus tan inverse of 7 over 7. So the answer would be 1 over 7 times, maybe I should give myself a little bit more space. So I've used this fact okay, I'll reference it after the video. I'll put it on the side. So I have some space here. I can just write the final answer. So I get 1 over 7 times tan inverse of 8 over 7 minus tan inverse of 7 over 7. And we've talked about how tan inverse of 7 over 7 is 1. So tan inverse of 1 is 45 degrees. But then 45 degrees is 180 degrees divided by 4. But then finally 180 degrees is just pi radian. So when we convert the degrees, we need to write them in radians. And this should conclude the problem. Very amazing problem. So this is just unbelievable. I cannot even think of this. This is what we used in this equation. And I'll just put a small box on here. There's the box. Now let's recap what we did. So we start with this very unsatisfying expression. We're like, okay, maybe we can do something with this. We bring it into this format with some nice observations about 14x. So we look at 14x, it's the key word. 14x is 2 times 7 times x. So it would be nice to have x squared plus 2 times 7 times x plus 7 squared. Because then we would write it as this. But then arises the problem of the 49. I write it as this, and it's nice. I can do a u substitution. the derivative of u, which is 1, is in our expression, so there's no problem in this u sub. It's actually a very healthy one. Then I reach this format, and then I'm kind of stuck. Then I think about my trigonometric identities. There's tan squared of theta plus 1. There's also sine squared of theta plus cosine squared of theta. This is more convenient if you have 1 minus something in the under the square root. So I tell you this beforehand. We've also given a brief hand-waving example about this. You look at your identities, you're like, okay, maybe I can bring this to be a 1, and then I can apply my nice identity. So I do that. I multiply 1 over 49 to get my 1. But then I can't just multiply by 1 over 49 from thin air, you know? So what I do is I have to divide by 1 over 49 as well. So I multiply and divide. It's like multiplying by 1. It's fine. Nobody objects. If I do it to the numerator and denominator, then it's fine. Then I proceed. So when I have this, I get my 1. And I need to adjust this because I need to make the right substitution. So I get this is 1 over 40. I get u squared over 49. I'm a bit careful and I turn this into u over 7 all squared. And then the venue is set up for me to make my substitution. When I do it, I get my sec squared. I get my tan squared of theta plus 1, so it gives me my sec squared. But I need to be careful because this is an integral and there are some other details. Like, for instance, the rate of change of u and the rate of change of theta. If I want to change this integral to be an integral in theta, then I need to account for the rate of change of u. So I do this, I take the derivative of both sides, I know this fact, so I use it. And then I write down my integral, and it cancels out very nicely. I simplify these constants. I integrate 1, so I get theta. And then I'm careful to substitute for theta. We know the tangent of theta is 1 over 7 of u. Then clearly theta should be the tan inverse of this thing. I use this, I plug it in. I just have from u is equal to 7 to u is equal to 8. I do it, and then I'm careful at the very last step to convert everything to radian whenever necessary. So that is how you do this problem. It is a very rich problem, and it is very difficult to master. What I would really encourage you to do is to try to take a break. This has been 33 minutes. It's a lot of time doing mathematics, at least just watching mathematics. Try to write down this problem and try to do it. Or maybe you can construct an example with your own hands. So you know that the keyword is with 7, so maybe you choose 5. So you make this 10x, and this is 49 times 2, so maybe this will be 25 times 2, because 5 squared times 2. Maybe this is 50. So this is an integral for you. You can try to do it and see what you get. And this should be very interesting. It should be something of the same format. And with this way, you're training yourself to tackle new problems. And it's also a very good practice to make up your own problems. It's a very strong one. But you should be able to reproduce this first before you try to tackle on any new exercise in the sense. And so this is really it. In the exam, this should not take you 34 or 35 minutes. Here we take everything at a very slow pace. So that is why we took us some time. But if we just know what we're doing, if we know how to think methodologically, and we know how to what the next step is, or at least we can figure out what it is, then we should be able to reach the correct answer in a record time.